Now I would like to welcome our amazing speaker for the session, Ovia Seshadri. Ovia is a respected research engineer at Coindcx, specializing in proof of work blockchains with a PhD in computer science and engineering from IIT Delhi. As the Chennai chapter lead for the Phoenix Guild, Ovia is dedicated to fostering the growth of the blockchain community. With extensive expertise and a passion for innovation, Ovia contributes to shaping the future of blockchain technology. Welcome, Ovia.
Awesome. Thank you, Bhavya, for that introduction. I hope everyone can hear me and see me. Yeah, I assume that's a yes. So feel free to keep posting in the chat, keep it lively, guys. And Bhavya is there throughout the call. So even if I don't see the chat, she will be there to point that out to me. So let's start, I guess.
So Ovia, before we start, we have a question. Why do we need JS syntax familiarity for this bootcamp? Will we be using JS for anything?
No, you won't be using JS in this bootcamp. So this is just an intermediate, beginners to intermediate level Solidity Bootcamp. But Solidity syntax is very similar to JavaScript. It also has some similarity to object-oriented programming like C++. So it's good to know JavaScript. You'll be able to identify Solidity syntax much easier. I mean, we said it's a prerequisite, but you will be able to follow this even if you don't know JavaScript. But it's good if you know JavaScript, because most of the good libraries for Web3 programming is built on JavaScript. So yeah, if you want to build apps after this, then if you know JavaScript, that's going to be of great help.
Amazing,
right? Yeah. So I think some people want to know if they're recording the session. I think that you are, right?
Yes, all these sessions will be recorded and shared on our YouTube channel. For updates, you can join the Slack channel and the Solidity Bootcamp Slack channel as well.
Cool. Okay, let's start. Let me just share my screen. Yeah, okay. Okay, so we're going to be seeing a lot of each other for the next 5 weeks. So it's time to get to know one another. Bhavya already told me a lot, told you guys a lot about me. I'd like to know what you guys also do. How you are interested in Web3. Do you already work in Web3? So please do share your introductions in the chat box. And after the session, I will go through them. Maybe towards the 5th week, I'll know you on a name-to-name basis. Okay, so and if you want to reach out to me personally on any for any doubts, you can contact me either on my LinkedIn or my Twitter handle, and my DMs are open. So, and I'm fairly good at replying to all of my messages. So, yep. So how are we going to structure this bootcamp? So this bootcamp is going to be for 5 weeks. 1 second, let me just, yeah. So this bootcamp is for 5 weeks, and in the first week, we're going to be doing a lot of theory work. We'll get the theory out of the way and then get to this fun stuff in the remaining weeks. So this week, as in today, we'll talk about Ethereum fundamentals. The next week, we'll start with hands-on Solidity. We'll go into the Solidity syntax and see how basic constructs work. The third week, we will go into contract-to-contract communication. And the fourth week, we'll look at some of the libraries and standards that are built for Ethereum. And for the 5th week, we will do we'll build our own contracts for some real use case. So that, yeah, and that's where this bootcamp will end. Today, as I said, we're going to be doing a lot of theory work. We'll start at the very beginning so that nobody is left out. We'll talk about what blockchains are, how they were formed, how they came into existence. You may think that you already know all of this, but it's actually fun, revisiting, refreshing all your basic knowledge. And I want to bring Solidity or bring Ethereum to you in a way that you can you can appreciate how the system is formed. I'll introduce different parts of the puzzle to you, and then we'll see how they all come together. And hopefully you'll be able to appreciate how intricate and what a brilliant solution this is. We'll deep dive into Ethereum, of course. We'll talk about the consensus protocol, which is the proof of stake, Ethereum virtual machine. And we have I wouldn't call it hands-on, but we'll create wallets for our work for the following weeks. And we'll look at how Etherscan works, what are testnets, faucets, and we'll start with what is Solidity. And if we have time permits, we'll go into what Remix is as well. I hope everyone is okay with that. So without further ado, let's begin. Okay. Right. Okay, something is happening. Oh, okay. Yeah. So all of you must have heard of the word blockchain, right? And most of you might have even worked on it. So you're fairly, you understand the concept very well. But it's a good place to start our discussion today so that we're all on the same page. A blockchain is, in my opinion, is just a data structure. It has data inside structures called blocks. Each block is connected to the previous block and forms a chain of blocks. And the first block obviously doesn't have anything before it, so that is called the genesis block. So this diagram, as you can see in this diagram, is just this chain of blocks. That's all you need to know. Each block contains some data. How this data is structured and for what purpose this blockchain is designed for is why we have different kinds of blockchains, right? Some of the other features are, you can store data and you can retrieve it. And since every block just appends, it's an append-only data structure, the history is preserved as it is. So anybody who can join this network at any point of time, download this entire blockchain, and they can see how this blockchain has grown from the very beginning and can be verified by them. So as a core philosophy of Web3, this blockchain gave birth to this decentralized technology. This is how we were able to realize this decentralized technology. So it is decentralized and distributed. As I said, it's just append only. You can't alter the history, and it works on public and private key. We'll get into all of these terms later on. So, but blockchain, even though, it's a big hype, it's a buzzword right now, right? For the past few years, it's been a buzzword, especially with Bitcoin and Ethereum and, very high trading prices. But if you break it down, the technologies that actually make it possible are not new at all. It wasn't a new invention. It was just a new way of looking at things, looking at existing technologies and putting them together. And in my opinion, blockchain has 4 core technologies that actually came together to form blockchain. So let's look at what they are. First is the P2P network. P2P is basically peer-to-peer network, right? The early stages of the internet, when it was first designed, was designed as a peer-to-peer network. A peer-to-peer network is nothing but a group of computers that are connected together in such a way that you have different paths of communicating between any 2 nodes. There is no one single path, and there is no one central hub or something that all the nodes have to access to get to another node, right? So there is no client server or market master slave architectures. So each node is its own client and its own server. You can get data from one node, and one node can also seek a data from the same node can also seek data from another node. So that is what peer-to-peer network is. And what makes it good is that it's dynamic. Any node can join the network at any point of time, and it can leave the network at any point of time without breaking the system. So if I break one node, only the connections with its neighboring nodes are lost. All the other systems are still able to function as they did before, right? And this ensures that there is no single point of failure. So if any node leaves or crashes at any point of time, the system, life goes on. So the second technology is cryptographic hashing. So these technologies have been there for decades. So, and blockchain has found a very innovative way of putting all of these together. What is hashing? Hashing is a mathematical algorithm. It's a function that takes one input and gives out one output. The input can be anything. It can be a string, it can be a number, it can be anything you want of variable length. And you give it to this function, and the output is a fixed size bit array, right? So any input that you give over here, you give it to the cryptographic hash function, and it always gives the fixed length output. Okay, and hashing has some important properties that we should understand. It is deterministic. What does deterministic mean? If you give input A to this hashing algorithm, it will always give output A. If you give another, so any number of times you give the same input, it will always give you the same output. That's what deterministic means. And it is irreversible. Irreversibility of hash functions is also known as pre-image resistant or one-way functions, which basically means you can get from input A, you can get output A, but from output A, you cannot get the input A back. So given this output, you will not be able to just even by performing this whole function or breaking down this function, you will not be able to get this input back. Even if you know exactly what this function does, and if you want to reverse engineer it, you will not be able to get this input back. So that is what the irreversibility property is. The third property is it is second pre-image resistant or collision resistant. That means if input A produces output A, you cannot find another input B that will produce the same output B. If that was a mouthful, what I mean to say is, if Fox gives this input, I cannot find any other input, no matter the length, that gives me the same output. So that is the second pre-image resistance. And avalanche property means that if you make a minor change in the input, it will lead to a drastic change in the output. So just let's recap all of these properties in a quick demo. So I'm just opening. Yep. Can you guys see this screen? Okay. So let's say I give my name Ovia. So let's look at the deterministic property. I give the name Ovia in this hash function, and it runs the hash and gives me this hash output, which is a hexadecimal, right? And if I change the input or something, the hash function changes. But if I give back the same input, Ovia, okay, so if I give Ovia, if you can just remember the last 4 digits, F4B7, and it starts with 56, ends with B7. Let's remember that. Okay, so let's go back. And then I come back to the same input. I get the same 56 and the B7. So we've proved this is the deterministic property. The second was irreversibility. Given this output, I will not be able to decipher the input. I can't show it to you in this demo. So let's skip that. And even this third property, we can't check in this demo, as in I can't find another hash function that gives me the same hash, that is 56 and B7. I can't find another input that gives me the same hash. I would have to try millions of inputs to prove this to you. But there are mathematical proofs for it if you would like to go check. And avalanche effects. This is one we can see over here. So let's say that I remove this letter I in my name over here. Just notice how much the hash function changes. Actually, every digit of this hash function will change if I just change one minor change of this. Can you see? So this is important because people cannot tweak the input to get the kind of hash that they want. Because one minor change in the input, even if I just add a space, the entire hash function has changed. So this is the avalanche effect, or the confusion and diffusion property. A small change in the input leads to a drastic change in the output. Now coming back to our, So I hope everyone is with me so far and we have no question. All right, continuing. So we looked at the second technology that kind of brought about blockchain. The third technology is actually digital signatures, but digital signatures are based on asymmetric keys, okay, around asymmetric encryption. So what is encryption? Encryption is basically the process of converting any message into a form that can only be read by a predetermined set of people. So you have a message, may the force be with you, which is called the plain text. Now you again perform some kind of mathematics on this function with two inputs. One is the plain text message, and the other is an encryption key that you have. Basically, you can choose anything as your encryption key, but you need to follow another algorithm to find the corresponding decryption key. So assuming you have a pair of encryption and decryption keys, you can give a plain text message and your encryption key to an encryption algorithm, and it will give you the output of an encrypted text. And the decryption algorithm is just the reverse of that. With the encrypted text, if you feed in the decryption key, two inputs, it gives you the original output back, which is the plain text message. So encryption is of two types. This is asymmetric encryption. The other one is a symmetric encryption, where both the encryption and decryption keys are the same. If the encryption and the decryption keys are different, then you have asymmetric encryption. Yes, Bhavya, you have.
Yeah. So we have a question. Batra is asking if we can get the original input Ovia from the hash.
Yes, that is not possible. That is the second property of the hash function, which is pre-image resistance or one-way functions, right? And just by seeing the hash function, even if you know exactly what the hashing algorithm is, you will not be able to retrieve the original input back in any form.
Got it. Yeah.
You can't even predict that it had 4 letters or it starts with O. You can't do anything. You have no idea what the input is.
All right. Okay. Interesting.
Okay. So moving on. So now let's get to digital signatures. So we know the concept of asymmetric encryption. That is, you have two different keys. One key is used to encrypt a plain text into an encrypted text, into a cipher text, we call it. And another key is a decryption key that converts the cipher text back into the plain text. So now that we understand this, digital signature is one very good use case for asymmetric encryption. With digital signatures, we are able to we're able to prove two things. One is integrity and the second is authentication. So, jumping ahead. Okay. So what is integrity, right? Why do we need digital signatures? See, digital signatures, you can compare it to just signing a document. Why do you sign documents? First, to say that you have agreed to whatever the document says. And the second part is that you are agreeing to it, nobody else is agreeing. Your signature is unique to you. So just by seeing your signature, people can say, yes, it is, the signature looks like my signature. I know people can, fake signatures, but so in digital signatures, that is not possible. So what I would do is I would take some kind of data, I would sign it in my with my some kind of signature algorithm, and I'll get the data and the signature. Now the signature is based on the data, so the signature will keep changing. It's not like one signature is it's unique for a person. Based on the data you're signing, the signature will keep changing. So with the data and signature, any person, the verifier, can verify that the signature is correct or not. And by verifying whether the signature is correct, you are proving two things: integrity. That is, that while sending the data from the signer to the verifier over the network, no middleman has changed the data in any form. If it is changed, then the verification function will just throw a false error. You'll just get some garbage value. that doesn't match. So it has proved that the message has stayed intact in the journey of it reaching the verifier. And authenticity is that only the signer who claims to have signed this message could have signed this message, because the signer uses the signer's private key, which is the encryption key, and the verifier has verified the signature using the signer's public key. Only if he uses the signer's public key, this data would have matched. It would have, the algorithm would have produced a true value. So that means that only the signer could have signed it. But you can ask me, then the signers, anybody who has the signer's private key could sign it and say that they are the signer. But it is up to the signer to keep his private key private, that he should ensure that nobody else knows of his private key, so that anybody actually verifying his signature can know that it is only from him. So I hope that is clear. We have another thing called non-repudiation, which is very similar to authentication. Non-repudiation just means that once you have signed something, you cannot deny signing it. You can't deny that, no, I didn't sign it. So which is another reason that signers should keep their private key very safe and nobody else can sign and impersonate them. Right. So the fourth and final technology is consensus. So consensus has been studied for a really long time. I mean, I think one of the earlier papers dates as far back to 1960s, 1950s. I'm not entirely sure, but it's a decades old field of study. So, but what is consensus? Consensus is just a group of people coming together and agreeing on something. It can be anything. It can be, let's plan a vacation together. When shall we plan a vacation together? And most often these consensus algorithms fail because we will never come up with the exact time on when to plan this vacation. So consensus is basically an agreement between a bunch of people. So it's a protocol, it's an algorithm. You follow a particular set of steps in order to reach some kind of conclusion. So consensus in this modern world has many applications. In the Web 2 setting, it is used a lot in distributed computing. And in the Web 3 setting, in case of trustless networks, we need consensus to agree on a state of a blockchain, right? If blockchain, let's say Bitcoin stores everybody's account balances, we don't want different people thinking that, different people hold different account balances, then the network would just not work, So this is consensus. So how would you basically, if you had to devise your own consensus algorithm, how would you do it, right? If, let's say, a group of your friends are coming together to decide when to meet for coffee. So what would you do? Maybe you're on a WhatsApp group together, and I would say I'm free at this time, and I'd post the message. And somebody would reply to that saying, no, I'm busy. Can we do this time? And then another person would again maybe rebut that and say, no, can we meet at some other time? So similar, to keep this process going, they would keep talking to each other. Everyone would propose new times that were not proposed earlier, and until they finally reach a conclusion. So this makes sense, right? We have all done this in our daily lives. So this is called iterative consensus. When a group of people follow a gossip protocol, they keep exchanging information and in iterative fashion in several rounds before they all agree on some common data. So this is iterative. This is a very, very secure, because you're making sure that the information is contained in your group, and that everybody who's participating in this consensus algorithm is satisfied. You only when everybody agrees to something, you finally end the algorithm. So it's very secure. It is optimal for smaller networks. If we have to decide something between 2 people, it's much easier than deciding something between 5 people. It's much easier than deciding something between, let's say, 100 people. right? So the smaller the network is, it's easy to come to an agreement on something. So that is why iterative consensus is good for smaller networks, but it always also occupies high bandwidth because you're continuously talking to each other in several rounds, exchanging information, and the network is busy throughout the execution of that consensus protocol till you reach an agreement. So this was very good. It's established, and people have been using it for a long time, but it is not practical in blockchain like technology, where yes, it's for trustlessness, it's good, but these blockchain networks are huge. I mean, there are thousands and thousands of nodes, so it is definitely not possible to make sure follow this COSO protocol till everybody agrees to something. So we go for something called non-iterative consensus. Hi, Bhavya, is there a question?
Yes, there are a few questions. So Avni is asking, does it mean that the signer's public used to decrypt the data? How does it work? Because we use private key to sign the data.
So the question is, can you just repeat the question?
Yeah, Avni is asking if the signer's public key is used to decrypt the data, and she wants to know, like, how does it work? Because private key is used to sign the data.
Yes. So as I said, the encryption key is the private key here in our digital signing example, and the decryption key is the public key. So the public key is known to everybody in the network, right? And the private key is kept secret to the original person. Okay, so let's just keep that in mind. Let's go to this screen. So you want to sign this piece of data. You have accepted that you want to send this piece of data, and you take your private key and you give it to the signing algorithm, which creates a signature. You just have to know, you don't need to know exactly what the signing algorithm does. It just know that it takes two inputs, data and a key, and it produces a signature. So the signature is unique to this data and this private key. Okay, and the encryption is done on this private key. So the decryption of using the corresponding public key should return the data back, right? Decryption using the corresponding public key, we should give back the original data. So remember that. So now the data and the signature has gone to the verifier. Now the verifier will independently take the data and independently take the signature. He will apply the public key to this signature, so it should return the corresponding data, right? So now you just check whether the two pieces of data are equal or not. If it is equal, then the signature is valid, otherwise it is not valid. I hope that clears your doubt.
Yeah, so there's a follow-up question that if anyone has the public key, they can decrypt it easily, right?
Yes, so the digital signatures ensures integrity and authenticity. The integrity means data has not been changed, and authenticity means only the signer has signed the data, but it does not ensure confidentiality. That means anybody can see this data and the signer is okay with it. Okay, if you want confidentiality, then another layer of encryption has to be added, so that only your only selected recipients can decrypt it. But confidentiality is not an objective in digital signatures, so we don't we're okay with this approach.
All right, so there's another question that how do we distribute the public key to be within our desired network?
So there are several ways to do that. So how blockchains do it, we will talk about it. But generally, there are things like certification authorities in Web2 settings. So you don't need to worry about how this public key is known to everybody, but just assume that. Let's look at, think of it like there's a telephone directory with all the public keys of everybody is listed, and you can just go and look up everybody's public key.
Yeah. Another question that is there is that what does it mean that signature changes with the data?
Right. So basically the signature is nothing but the encrypted form of this data, right? So when you give different data, then you will get a different encrypted text. So that is basically your signature.
All right. So the data that we are signing actually affects the signature, is it?
Yes. So we are calling it signature, but it is actually encrypted text. This is the encrypted text, is the signature. So if I give different data, then this will look a little bit differently.
Got
The
it.
key is the same, but
Yeah.
as the text changes, then the encrypted text also will change.
Okay, sounds good. Another question that we have is Sinus private key is the same private key that you can export from MetaMask, right?
Yes, that is. We will see how that is. So I have explained these technologies to you, and it's beautiful how they are used in the blockchain. So I would like you to understand these at a conceptual level and recollect them when we talk about blockchain and the specific use case that they used it.
All right. Yeah. I think that is all for now. We can
All
continue.
right. Okay. So we were talking about consensus. There are no questions about consensus. So we were talking about non-iterative consensus, right? So I hope everybody understood the example that I gave for iterative consensus. A WhatsApp group, you're deciding on a time for coffee. So now as the people in the WhatsApp group increases, it's very difficult to come to a consensus, and it's going to take a really long time. So for these kind of scenarios, we go for a non-iterative consensus. Consider our own government, for example, right? If let's say a law has to be passed in our country, we can't go and ask every citizen of the country if they accept this law, or first it'll take a lot of time, and most people are not aware enough to have a say in the law. So what we do is we elect somebody to make the decisions for us, right? So that is how non-iterative consensus work. It's an election-based consensus, where there is a quick election round where one person is elected as a leader, and they propose something, and everybody has to just accept that. So this is also practically used in our everyday life. So in this form, here you take very less time and less bandwidth because the election protocol is very quick. And after that, you just accept whatever the leader says, and it's used in most blockchains where the network size is so huge. Right? Okay. Okay. So now consensus is not an easy thing to implement because of several things, right? You have to be fair to everybody. Just because a leader is elected, he can't make malicious decisions that adversely affect the others in the network. So you have to be be fair. Yeah. There's a question.
Yes, I have a question. If non-iterative consensus is decentralized or not?
Yes, so that's where so the election protocol that I've described, right? So that is what makes it decentralized. So I will explain the protocol to you, and you tell me whether it is decentralized or not.
All right. Another question that we have is copy of state of blockchain for every node same as consensus?
So the copy of the blockchain is what you are arriving at a consensus on. Like I said in the WhatsApp group, you're arriving at a time to meet for coffee. Here, you're deciding on the state of the blockchain. Let's say that I have 10 Bitcoins and Bhavya has 20 Bitcoins. This is the copy of the ledger. Let's just say two people who actually have money in the network. Everybody else in the network should agree that I have 10 Bitcoins and Bhavya has 10 Bitcoins. This is the state of that blockchain. So if this data should be the same for everybody on the blockchain. So that is the thing that we are arriving at a consensus on.
Right. Yeah, please continue.
Right. Okay, so as I said, it's a very difficult thing. Firstly, we have to be fair. We need to meet everybody's expectations. And even if there are adversaries, some kind of malicious player who's trying to disrupt the process, we should ensure that even we have some tolerance towards the adversary. Just with a group of 100 people, and if one person is malicious, like shouldn't be like the whole consensus algorithm fails. Right? And we should cater to geographical distribution and delay. What I mean by that is, if we're all in the same room, it's easy for us to come to a consensus, right? Because the bandwidth, As soon as I say something, the other person is going to listen to it and immediately I'll get a reply. But imagine if two people are on the opposite ends of the world, if they have, and we're following the gossip protocol of iterative consensus, one person says something, takes time to reach the other person, and the other person, replies something back, and that takes time, or something happens to the message and it gets, it fails. So we need to keep in mind all the things that could happen. So the geography, with wider geography of the players participating, we have to accommodate for more time. And dynamic networks. Okay, so another factor of why consensus is difficult is dynamic networks. What I mean by that, in iterative consensus, all of you are there in a WhatsApp group. You know there are only 5 people there. Nobody is going to leave, and after you've reached a consensus, no new person is going to join and disrupt the whole data that you've arrived at a consensus on. So, but in blockchain networks, it's not like that. Anybody can join the network and leave the network at any point of time. So you should have a consensus algorithm that is so strong that even if somebody joins at a later point of time or leaves the network during a consensus algorithm, you still reach consensus. It's not like everybody else is stuck because one person leaves. Yeah, so, and again, scalability, right? You need to be able to cater to thousands and thousands of nodes and arrive at a consensus quickly and efficiently among all of them. So, birth of proof of stake. Okay, so so now I'm going to introduce the how Ethereum works and how consensus is achieved over here. So as I said, all blockchains, okay, I should say most, just to be safe, follow leader-based consensus, which is non-iterative consensus. So we divide into epochs. Let's say that we want a block every 10 seconds or every 30 seconds. So every 30 seconds, there are a group of nodes, or I'll call them validators. Validators are basically, in the P2P network, we saw different nodes, right? So in Ethereum, they're called validators. So the validators, regardless of all that, there are a lot of transactions. There are people participating in the network, and there are a lot of transactions. So what we need to arrive at a consensus on is what transactions have happened that changes the state of the blockchain and in which order they have happened. So this is what we need consensus on. A lot of peers are broadcasting transactions parallelly. That is just happening in the network. There's a lot of noise. Now, there are special people called validators who are actually the nodes forming this peer-to-peer network. They collect these transactions and put them into blocks. So locally, everybody is forming different blocks. These blocks need not be same. They need not have consensus among them. Individually, I see some transactions. I have collected them into blocks. Now, these validators will also participate in an election protocol called proof of stake. Now, we will see what proof of stake is. For now, let's assume that the proof of stake will output one person as the leader, or we call them proposers. So if that validator wins the election, they are called proposers, and whatever block that they have created, they are allowed to broadcast that block to the rest of the network. The other validators who lost the election now have to accept the proposal. Whoever won that election, they have to accept that person's block. They receive that block, but they can't blindly accept. The transactions that person, the proposer, has included in the block has to be valid. So they will verify the proof of leadership. That is, yeah, that guy did win the election. And second, they verify all the transactions that are there in the block, and then substitute that changes in that order in their local state. So they update the state of their local blockchain, and then they continue mining. So the round repeats again. So then they move on to the current block and they start mining. Then they participate again in the consensus protocol, and it repeats. So this is how a new block is added onto the blockchain. Just to summarize again, there are nodes are called validators. Validators will participate in the consensus protocol called proof of stake that elects a leader. The leader will broadcast. So the leader will broadcast their own block to the rest of the network. The other validators will pick up that block, verify the whether the leader has sent it, and verify all the transactions, that they should have also received those transactions, right? And they will execute it in the order that the leader has proposed, and they will update the state of their local blockchain and repeat this process repeats. So this is how a new block is added to the blockchain. So yeah.
Yeah, so we have a question. Validators are humans, so how are they selected and how are they held accountable? Does this not make the system untenable beyond a certain scale of size or latency?
Yes, validators are humans. They are basically not sitting and listening to transactions, or they're not doing any manual work. Basically, they've started a piece of software that is running on their system, and that software does everything for them. But yes, software can be changed. They can do some malicious code. But if they do malicious code and if they win the election, we'll assume that the network is resistant to at least 50%. Like only if there are 51% people acting maliciously, the network will fail. Ethereum network is tolerant to up to 50% of malicious nodes. So if a guy is malicious and he broadcasts his block, the majority of the node is still behaving honestly, right? So they will validate whatever he said in the block, and then they will reject or accept the block accordingly.
Right. I think there's some confusion between consensus and protocol, because there's another question. They're asking validators will be selected by who has many tokens of crypto, or how are they selected?
No. Well, that's why. Okay. So every node. So we studied. We saw what P2P networks are, right? So in P2P networks, all of these are nodes, and in Ethereum we call them validators. So how the process of becoming a validator, I will explain. I'll explain what that is. Now, among these validators, one person is elected every few seconds as the proposer. And the proposer will send his block to all the other validators. They will verify it. And then after that, he becomes a normal validator. Again, somebody else is chosen as the proposer. So this is how it works. Now, so we will see how one validator is chosen as the proposer and how a normal person can become a validator in the upcoming slides.
Perfect. We have one more question. If a particular transaction in block is not valid, is the entire block considered invalid, or the invalid transaction is removed?
No. How if let's say that you remove the invalid transaction, everybody should follow the same thing, right? All the validators should. They're all behaving locally, right? They are just following an algorithm. They are not talking to each other. So if I receive a block and I find that one transaction is not correct for me, then everybody else should find that same transaction invalid for them. Maybe I have just not received this transaction in my local system and everybody else has already received. So they may accept the block and I may reject it. So it's all or nothing. If I think that everything in the block as I received it is perfect, only then I accept it. Otherwise, I reject the whole thing.
Yeah.
And so similarly, some people may reject and accept. Totally, the block is only accepted if the majority of the validators have accepted the block.
Got it. Yeah.
Any other questions?
None as of
now we have two important questions to answer. How do you become a validator? And once you're a validator, how do you become a proposer, right? Okay, that's where we enter proof of stake. But one thing I just want to mention in this slide is that notice how we have very smoothly introduced the concept of decentralized storage, right? We should appreciate this, because now we have enabled a kind of system where there are so many validators who are just following an algorithm, but at the end of the algorithm, they're able to store a blockchain state in their computers, in their local computers, that matches the blockchain state of every other validator, be it 1,000, be it 1,000,000, it'll always match. And they have, and we're able to store somebody's balance on all of these computers. right? So this is decentralized. There is no server that is giving us this data. We're just following a set of rules, and we're able to maintain that data. So I think it deserves some appreciation. Yeah. So just make a note of that. We now we're able to store data in a decentralized way. Okay. Now proof of stake. What is proof of stake? It is a consensus. We call it a consensus algorithm, but essentially it is just the leader selection algorithm, right? People participating in proof of stake, that is the validators participating in proof of stake, will ultimately, be nominated as a proposer or not. That's what proof of stake does. Earlier, we had, just before proof of stake was something called proof of work that Bitcoin used, and that consumes a ton of energy. So that's why, Ethereum said the concept of proof of stake was actually, I envisioned much long ago, but it was implemented in Ethereum very recently. So proof of stake came after proof of work just to avoid this energy consumption. But let's see, I don't want to go into proof of work. Let's see what proof of stake does. Proof of stake is exactly what it means, right? If our objective is to elect a proposer from a set of validators, and I'm saying that I will select somebody as a proposer who has most stake in the system. That is, who has invested so much in the system and cares about the growth and well-being of the system that they will not act maliciously to propose a block. Is the ethos of it clear? So proof of stake basically means you're electing a proposer who has a lot of stake in the system in belief that he will not behave maliciously because his stake is there in the system. So if the system goes down, he goes down with the system. So that is what proof of stake does. So here they don't receive any block rewards or anything, but any in the block, all the transactions that they add, they have some transaction fees that they can claim. So there is some reward or incentive to be a proposer. That's why many people want to become proposers. Yeah, but to become a proposer, you'll have to also put money into the system. But it is like proof of work, it doesn't cost much energy and all, and the election process is very simple and it's less time consuming. So this is how proof of stake works. Let's see how validators are chosen. So as I said, you have to have stake in the system. So to have stake in the system, even to become a validator, you have to put stake. So in Ethereum, so I think this data I collected some time back. I don't know if it is still exactly the same now, but I think the conceptually it will be the same, but the exact numbers may vary. So the validator running an Ethereum node has to deposit 32 ethers. We'll talk about what ether is or what this actually means. Let's just call it dollars. Yeah. Okay. So the validator, to become a validator, I have to put 32 ether, which is a large sum of money. I mean, somebody can maybe calculate it in terms of INR or dollars or in your local currency and tell me what 32 ethers value is today. So they put 32 ethers, and on depositing that 32 ethers, they join a waiting list of validators. And periodically that waiting list goes up, and finally they're accepted as validators on the network. Yeah, Bhavya.
So we have questions. They're asking if stake means NFT or any token based on the network or the platform.
We have not talked about tokens at all. Don't get ahead of yourself. We'll cover all the jargons in due course. We have 5 weeks together, but just think of it as some money. In Ethereum, there is a native currency called ETH. So they're going to pay in ETH, right? This is the only way they can pay. They can't use any NFTs or tokens.
Another question that we have is how the validators know that there's a block that needs to get validated. Do they receive a notification from the network?
right? So they've all participated in the election protocol. That is proof of stake. They know whether they won or lost. If they are a proposer or not. If I'm a proposer, I'm just going to broadcast my block. If I'm not a proposer, I'll wait for someone else to send me the block.
Another question that we have is, what is stake and what is proof of stake?
Right. So proof of stake is the election protocol that we are using to select a proposer from a group of validators. So that's what we're talking about, how that happens right now. So we have a set. Is there another question?
No, that's all.
Okay. So now that you've become a validator and you've entered the system, that you're a node on this P2P network, which is the Ethereum blockchain. On every epoch, one validator is chosen by different factors. The amount of ETH he has staked, staking age. So let's say that I have won in this round. I have won. I'm a validator and I've become the proposer. I have staked 32 ETH to become a validator. When I become the proposer, the age of that 32 stake becomes 0. What I mean by that, the 32 ETH is not destroyed. My money is still there, but the time in which the money has been in the system, right, that is reset to 0. So the oldest validator who has the maximum stake will win the protocol, will become the next proposer. And if there are two people with the same age and the same stake each, we use some kind of randomness. Maybe we look at their addresses and take the smaller address. Some kind of randomness is added if there are more, if there is ambiguity on who's exactly the proposer.
Right. I think they're asking more about what essentially does stake mean in simple language.
Stake.
There are a lot of questions about it.
So you must have seen movies, and so in any big organizations, you have a boardroom of committee members who are basically stakeholders, right? They have stake in the company. They are allowed to make decisions for the company. Anything that happens to the company, they have to approve it, or they are asked for their advice. So everybody who has stake in the company are able to make a decision for that company. Similarly, everybody who has stake in the Ethereum blockchain are allowed to make decisions for the Ethereum blockchain. Does that make sense?
Yeah, perfect sense. Yes,
Okay.
I think you continue. We have one more question. Is it possible the same validator will become the proposer always?
No, that's not possible because the staking age is reduced. So Ethereum blockchain has matured to such an extent that there are so many validators in the system, and on a high level, it goes in a round robin fashion. So once you become a validator, it takes a long time for it to come back to you. You in your lifetime, you will become a validator proposer more than once, but it's going to take some time.
Perfect. Yes, I think that's all we have for now.
Okay, cool. So yeah, so in every slot, a committee of validators is chosen, and then right. So what this is basically saying is, in every epoch, a proposer is chosen from the set of validators. The proposer will propose a block. The transactions are delivered and re-executed. Note that point. Every single validator on the network is re-executing a transaction. This is a good thing and a bad thing. We'll talk about it later. After re-executing, then they will cast a vote on that block. That is, if I'm a validator and I accept the block, or I reject the block. If a majority of validators accept the block, then the block is there in the network forever. So this is how Ethereum blockchain grows. Okay, so Ethereum has distributed consensus, right, via the non-iterative consensus protocol called proof of work that we just discussed. It has decentralized storage. Through this consensus, we're able to accept the state of a blockchain and maintain it. So everybody has the same data in any point of time, right? So we've achieved decentralized storage. Bitcoin only offers these two. It offers distributed consensus and decentralized storage. That is, the storage part is basically the balance of everybody's account. But Ethereum went one step ahead and gave us decentralized programmability. That means if you're able to store somebody's balance, then you should also be able to store a piece of software or some code, right? If I can ask you for the balance, I can also ask you for a result after giving you some input to run that code. I hope it is sinking in of what a big leap this is. So from decentralized storage, we are going into the realms of decentralized programmability, which is like the cherry on top that Ethereum gave to the world. And so actually this was thought of by Vitalik Buterin, who's founder of Ethereum. And he was actually a Bitcoin community contributor who thought of this and then started his whole company called Ethereum. Yeah, there's a question.
Yes. So Nived is asking if staked ETH has any significance in voting power while voting for the validity of a proposed block.
Yes. So staked ETH definitely has power. The more you stake, the more power you get. Like I said, the highest stake with the highest age will be given the chance to become the proposer. But that does not mean the rich will always get the power, because there's an upper cap of 32 ETH. And 32 ETH is a really large amount. Most people might not be able to afford it. But really rich people can have several nodes with 32 each, but they won't get, in the round robin fashion, they won't get the chance more than once in some time.
Yeah. This is another question. If you can give a short description about, again, the differences between the proposer and the validator.
Right. So as I said, we're talking about an election. So let's take an election example. So we have BJP, Congress, Aam Aadmi. These are all validators. And the election is the voting process that we do, the ballot vote casting system. And then whoever wins that, whoever gets the maximum votes, is the prime minister, or the party forms the government. So that party is the proposer. Is that a good metaphor?
Please let us know if that answered your questions. Yes, for clarification, these are all different political parties in India.
Oh, I'm so sorry. I keep forgetting I'm talking to a global audience. Yes.
Someone is also asking that means that everyone in the network has equal voting powers, right?
Everyone in the network has, all the validators have equal voting powers. That is, if I say the block is valid, that is one vote. If any other validator also says the block is valid, that is also counted as one vote only.
So it's not dependent on the stake date.
No. All validators are equal. The staked ETH only comes into play when you're choosing the proposer.
Yeah. Yes, that's all we have for now.
Awesome. Let's move on. Okay. So from decentralized storage, we're moving into decentralized programmability. And let's see how that changes our world. Okay. Before talking about this, decentralized programmability, that's what we're here to learn. This is literally the objective of the course, to learn a language that offers decentralized programmability. So decentralized programmability basically means the data that you're storing on the blockchain, instead of transactions that just says this person has this amount of money, you're storing a piece of code that can be executed by anybody on the network. Now, so this code is basically called the smart contract. So now there are a lot of problems with having people in the network store a piece of code, because different people write code in a different way, and then attacker also can write malicious code. So we don't know exactly who's writing code. Are they even capable of writing good code? And what if, the code just depletes all your resources when you're running that piece of code? What if it, introduces a bug in your system, or just crashes your system, blocks all your memory? Or what if it's just running an infinite loop, clogging your CPU? So every validator on the network, they're all maintaining this copy of the code, right? And if asked to execute it, they should and produce a result. So when they're executing, we should protect the time and resources of these validators, right? You can't really verify the code, but you can put limitations on how the code should be executed such that you never run into a scenario where the validators are left where the system has crashed or their memory is full or their CPU cycles are clogged. So you should not let the validators go into that position. So you have to put some limitations on how on the execution of this code. Yeah.
So the question is about how decentralized storage is different from cloud storage and what makes it really decentralized.
Right. So decentralized storage, what I mean by decentralized storage is, let's take the Bitcoin example where everybody in the account has a balance and that is the data you want to store, right? Now, we have just discussed a way in which everyone can maintain that data without talking to each other, and you don't care about the size of the network. So there is no server. You're not asking somebody, please give me Ovia's bank balance or Ovia's account balance, right? You're able to, just by following the steps, just by looking at the series of blocks from the beginning, you're able to determine my balance and you have a local copy of it. This is decentralized storage. What does cloud storage do? Cloud storage is somebody is running a server somewhere and they have given some space to you to store your data, right? But it is still their infrastructure. They can take it down at any point of time. They can delete your data. They can manipulate your data. And of course, they say that there is authentication and there is some level of trust that they have gained from us over the past years. And we have also given up a lot of control because they're offering free services to us. So there are pros and cons, but it is still very much in their control to do whatever they want if they choose to do it.
Right. Yes, that was all.
Yeah. So like I said, we are going in decentralized programmability. We are storing a piece of code in somebody's system, and we have to ensure that the code is written in a safe way so that when executed, it doesn't deplete their resources. So now, in order to do that, the solution to make sure that the resources are not depleted is to ask the person who wants the code executed for money. So if you put a price on every time the code is executed, then you can ensure some kind of fair transactions or fair execution of the code. So to first put the price, we need to know how to get that money. And in Ethereum, we use a native token called ETH or Ether. The symbol is called ETH. This is the token that we always see, but it has denominations up to 18 levels. So a dollar can have 100 cents. A rupee can have 100 paise. So similarly, ETH can have 10 to the power 18 weight. So this is the denomination for a ETH, for Ether. And an intermediary level is GUE, which is also a denomination. A GUE is 10 to the power of 9 weight. Right, so these are the denominations in which we can claim the price for executing a transaction. So the price for executing a transaction is called gas. So I think we have already overshot time. I still have a lot to discuss. How do we go about this? Bhavya, could we take another 20 minutes or so if everyone is okay with it? Or I'm sure I would like to finish it this week, so then we can start the coding part next week.
We can definitely extend this session, or we can schedule another one tomorrow, whatever suits you the best.
I think we can finish it off now and it will be recorded. Yes. So people who have to drop off, feel free to watch the recording, and you can post your questions to me or Bhavya, and I will make sure I answer them. Does that work?
Yes, that sounds perfect. In
Okay.
case you have any doubts, you can drop them either on the Slack channel itself, or you can directly text Ovia over her socials. Those are all shared in the Slack channel.
Sure. Okay. So I'll just take another half an hour if that's okay.
Yeah.
So
Yeah.
now we've introduced the concept of gas. Gas is a way to charge someone for asking a validator to execute the transaction. So remember, a transaction is broadcast in the system. Let's go back to this slide. Yeah. A lot of transactions are broadcast in the system, and every validator is executing that transaction. So anybody who wants the transaction to enter their blockchain has to set an appropriate gas, it has to pay for an appropriate gas price to protect the validators when they're executing that transaction and verifying it. So let's come back to what gas is. So it's work. Yep. So anyone who's sending a transaction on Ethereum needs the validators to verify it and update their local state, has to pay gas. So many use cases of this is it limits spam. So transactions that cannot afford to pay gas will not be included in the blockchain. So you can severely limit your transactions to only the useful ones. That increases security. It also increases the performance of processing algorithms. You get through many transactions in unit time. So it limits the number of steps of execution, basically. That saves costs. It also compensates for the person, the validator, for their computing power and the resources that they have used, basically. So the gas has several components. The gas limit. Now, the proposer, we said that the proposer is sending his block, and proposer is forming a block with a lot of transactions in it, right? Now, every block has a gas limit, and this is a fixed amount that every Ethereum block can only hold this much number of transactions. That is, the sum of the gas of all of these transactions should not exceed some upper limit. That is called gas limit. Gas used. Every transaction has some gas, right? So gas is basically, let's say that I'm adding two numbers, 1 plus 1 or something. Just adding two numbers, A plus B. Now, the cost of execution, the memory cycle or the opcodes that this translates to will use a particular unit of gas. Let's say it costs 10 units of gas. This is just a very vague number, which is nowhere close to the actuals. But let's say adding two numbers costs 10 units of gas to run in the validator's system. So every transaction, if the transaction is just adding two numbers, it is just 10. Maybe it has adding some numbers and subtracting some numbers and doing all of that. That will cost more gas. So this transaction, based on the complexity of this transaction, this will be the gas used for that transaction. Now, for every unit of gas, let's say I said that adding two numbers costs 10 units of gas. For every unit of gas, the person sending that transaction has to fix a price for that 1 unit of gas. So one person may be willing to pay, let's say, like 100 GUI for his gas price, and another person not so rich, maybe, or maybe the transaction is not important enough, will only be willing to pay, can only afford to pay 10 GUI for 1 unit of gas. So based on that, can you see how each transaction can be more benefit, can cost more or less? They may actually cost the same unit of gas, but the price for each transaction may vary based on the gas price that the transaction initiator is willing to pay for each unit of gas. So the total gas fees is nothing but the multiplication of the two. The units of gas used into the price per unit of gas. So this is the total gas fees, and that can be claimed by the proposer. Okay. So now, as I said, every transaction in Ethereum requires a certain amount of gas to execute. There are different operations that cost different amounts of gas. When I say gas, I mean gas unit is different from gas price. Yeah, please, Bhavya. That's a question. Okay. I can't hear you. So I'm going to continue. The proposer proposing the block cannot exceed a gas limit. The gas limit has nothing to do with the gas price. So obviously the proposer will try to add the transaction that give the highest gas price so he can maximize his rewards. So that is the gas limit per block. Right. Okay, so let's say that I have quoted an incorrect gas. Okay, maybe we can talk about that a little bit later. Okay, you have to optimize gas. You don't want to pay unnecessary. Hello, Bhavya, are you there? Hello? Hello, Bhavya? I think she has been dropped off. Let me just. Hello? Yeah, I think she's joined back now. Bhavya, can you hear me?
Hi, yes, I think there was some network issues.
Okay. So no worries.
So we
Okay.
have a question. People are asking who fixes the gas fee?
You fix the gas fee. You know that you have to execute a transaction. The gas units for that transaction is fixed. Let's say you have to add 1 plus 2 numbers, then it's definitely you need 10 units of gas. But it's up to you to fix the price of that gas such that your transaction gets accepted to the proposer. The proposer will obviously want more money, more rewards. So if you give higher gas price per unit, then your transaction is more likely to be accepted into a block at an early point of time by the proposer.
So how is the minimum gas fee decided?
Minimum gas fee. So as a user, any wallet provider that you go to will kind of set that amount for you. So you don't have to worry about that. But if you can even say that I'm paying 0 gas price, you can say that, but nobody is going to add your transaction to the block. Right. So, or it's going to take a really long time to add your transaction to the block. So based on how early you want the transaction entered into the blockchain, you can tweak a setting in your wallet provider. Let's say you're using MetaMask. MetaMask will estimate 3 prices for you. It will say if you pay this much and if your transaction is going to enter in the next 3 blocks. If you pay this much, then the chances are it will enter only in the next 10 blocks. Does that answer the question?
Yeah, that answers the question.
Yeah. So again, you have to write your the code that you that is there in the smart contract should be very efficiently written, such that it doesn't require so many units of gas to execute. So when you reduce the units of gas, automatically gas fees reduce. So that's how you try to optimize gas, by writing good code, and try to avoid pushing your transaction when everybody else is also trying to push their transaction, because gas price will keep going up at that point of time. So look for a time where the network is very calm and not so busy, and you'll get cheaper rates at that time. Right. Okay. Okay. So now we're coming to the EVM. So now we said that every validator is executing the transaction, right? How does he execute? The environment in which every validator is executing these transactions is called the EVM. EVM is Ethereum virtual machine. We already know what virtual machines are. What's a virtual machine? It's like an operating system, right? That runs on another operating system. It has some set of CPUs, memory, storage disk, all your operating system fundamentals. So now EVM is just like that. It has its own CPU, which is it has its I shouldn't say CPU, some kind of processing part. It has some memory parts, and it has counters. So it basically functions like any other virtual machine. So, but the objective of this is to maintain this blockchain state and follow this whole consensus protocol and verify the proposed transactions, etc. So let's say that a transaction has come in, which is the code part, and it has to be executed. The program counter will basically go line by line to execute this piece of code. And every time, so when a transaction comes in, the gas available for that transaction, right? So let's say 10 units of gas, addition of some of, actually addition is transfer functions at 20,000, 21,000 units. But let's go with our 10 units example. So the available 10 units is set over here. Every time a function is performed, right? Some operation is performed, some gas is consumed. A call is made, external call is made, some gas is consumed. Every time a gas is consumed, this keeps getting deducted until it becomes zero. If it becomes zero and the code has not finished its execution, right? It is still somewhere here. The whole thing is reverted. The gas that is already consumed is deducted from the user and the transaction fails. But if the transaction has finished executing and there is still gas remaining over here, that is refunded back to the person who has initiated that transaction. So this is how the Ethereum virtual machine works. So,
a question, what is a smart contract?
A smart contract is basically a piece of code that is stored in, that you can ask that you can send as a transaction on the blockchain, and it is stored on different validators. Everybody maintaining the state of the blockchain stores it in their local systems. So if you want that code to be executed at a later point of time, you can invoke a function from that smart contract.
Yeah, I think so.
Right. So just to clarify, smart contract is a piece of code. It is a set of functions, right? You know what functions are if you're a programmer. Function is basically a set of steps that takes some inputs and returns some outputs, right? That's a function. So a smart contract is a set of functions, and you can store this code as a transaction on the block, on everybody's local state of the blockchain, such that at any future point of time, you can invoke one of the functions of the smart contract. Okay, so as I said, every operation, so computational operations will consume gas, storage operations will consume gas, memory operations will consume gas, contract execution, we're doing an outside call, flow, like if else statement, loops, everything will consume gas. And it's okay till you have gas available. The minute the gas available becomes zero, the transaction. So this is how we protect the validators. So the whole concept of gas, as I said, was to protect the resources of the validators. So this is how we ensure that the resources are adequately paid for the resources that they use, and that the code is also not written in a malicious way, because if it was written in a malicious way, the whole thing gets cancelled and the person's money is wasted, right? So he should write proper code so that the validators' resources are not wasted. I hope that makes sense. Now, Ethereum. So we've spoken a lot about transactions and how EVM works and what is consensus and all of that. Now let's look at how a person is identified on the Ethereum. So in Bitcoin, we know that I have an address and that address has some balance, right? How does that happen in Ethereum? Same way, Ethereum also has an address, and each address can have some balance. But there are two types of addresses that is possible on Ethereum. In Bitcoin, we didn't have any smart contract, or we didn't have that decentralized programmability aspect. So every account was basically, the Bitcoin account can be compared to the externally owned accounts in Ethereum, where there is just some address and a balance to it. So now that we have smart contracts, we allow the smart contracts also to have a balance. So this is the second type of account that is possible in Ethereum, called contract accounts. So there are two types of accounts: externally owned account and contract accounts. Externally owned accounts are accounts held by people or organizations that have a private key associated with it. Going back, relate to the asymmetric encryption that we spoke about, where everybody has a private key and the public key is known to everybody else, and they can use to digitally sign messages using that private key. That is exactly what this is. Every externally owned account has a private key that is known only to the person holding this account, and the address of this account is basically the public key, the corresponding public key. Right. So this is the externally owned account, and externally owned account has several properties. A balance is one of them. That's how we maintain the balance of this account. The contract account is little bit different. The externally owned account is secured by the private key. Anybody who signs using this private key only can transact from this account. But in contract, there's nobody owning that contract. A contract is just deployed onto the network, and it just exists on the blockchain, and anybody can execute it at some point of time. So how do you secure this contract? You have to secure it with the code that the contract has. And it also has a balance field. That is, the contract also can have associated balance with it. Yes, Bhavya, is there a question?
Yeah, so there's a question that if a transaction fails, the gas is already consumed. Is it refunded or not?
No. You have to set appropriate gas units for your transaction to ensure that the transaction completes fully. If it fails, whatever gas is consumed till that point of failure is gone.
There's
So
another
make sure that the transaction doesn't have any bugs in it or no runtime errors. So if the code, basically the transaction is some code execution, right?
Yeah.
You're running this piece of code. If you have a runtime error here, it will execute till this point, or there is some gas that is consumed till you reach that point, that is used, that won't come back. Whatever is left maybe will be returned to you. So make sure that you test before deploying anything. Yeah.
So there's another question that at all times, if the smart contract function call was failed in middle of the execution, does the money get refunded or not again?
Yeah, again, if it fails in the middle, whatever resources were used till up to that point is consumed. It is not returned. If it is a runtime error, that means the halt happened sometime somewhere in between. And if you still have gas available, then that is returned to you. But if it is, let's say, an infinite loop or something that just goes on and on and on, at some point the gas will become zero. And the contract is also not finished execution. So nothing is refunded to you, and the whole transaction is also cancelled. It is reverted.
Got it. There's a follow-up question on this. If we select low gas and if no one attempts to validate, will the transaction go into pending or will be failed?
So if there is low gas, so there are two things. If you put low gas, the proposer who's proposing the block may not even add your block to his, add your transaction to his block. So that is one thing. That means it's pending. Nobody is willing to add your transaction to their block because you're not paying them enough to do so. Okay. So in some rare case, the transaction has been added by the proposer. He has accepted the price that you're offering, and it's been added to his block. Now it has come to the validator for verification. So in the validator, each transaction the gas units that you have claimed is not in your control. That the wallet provider will, based on the number of instructions, it will be decided for you. So it's very rare that unless you go and meddle with the system, there won't be a scenario where a wrong gas estimation was done such that a valid transaction will fail to execute in between because of low gas units.
So another follow-up question on this is there any time limit for for the person to add it on the transaction? And how does the gas limit get decided? Is it decided by the network?
Gas limit is predetermined. That is, let's say that every block can hold up to 1,000 units of transaction worth 1,000 units of gas. You can have 100 transactions of 10 units each, or you can have 10 transactions of 100 units each. Doesn't matter. So I am saying that each block can only hold 1,000 units of gas. totally in all the transaction it has. So if somebody, if a proposer wants to include one transaction of 1,000 units of gas, which is paying him a very high gas fees, he'll just do that and get his job done. Does that answer the question?
Yes, that's all we have for now.
Okay, cool. Yeah, so this gas is a kind of difficult topic to get your head around, but once you understand it, it really makes sense. So we were talking about different types of accounts in Ethereum. One is the externally owned account that is secured by the private key, and the contract account, which is secured by the code that it holds. The contract account does not have a private key, so the transactions or anything cannot be signed here, right? So these are the different two types of accounts. Externally owned accounts, in future, I'll call them EOA. That's how the community also refers to these accounts, EOA. One more thing to note is that, so the contract, so I said the externally owned accounts public address, right, is basically the public key, right? So how does the contract accounts address look? It looks identical. Just by looking at two addresses, you cannot determine if it is a externally owned account or a contract account. Like in layman terms, we cannot distinguish, but a validator will be able to distinguish because he stores the state of the blockchain. So now the externally owned account cannot sign transactions, and we know that all transactions have to be signed by somebody because somebody is there to pay the gas fees, right? So contract accounts can never initiate a transaction. Any transaction that has to come from some externally owned account who is capable of signing that transaction. Externally owned account can invoke transactions that call a contract, or it can call another externally owned account, or a chain of contracts, doesn't matter, but it always has to initiate from an externally owned account. All transactions in Ethereum has to initiate via an externally owned account. Right. So now, as I said, there is some transaction that has to come from an externally owned account. The externally owned account will basically set the gas supply, with a gas price. And we are kind of abstracting all the intermediate things that happen. That is, the proposer will accept the block and all of that. Finally, we'll assume that this transaction has come to the validator to validate, and that validation process is invoking some contract function. So the contract function is executing some code, and that is consuming gas. If there is some gas remaining at the end of execution, that is just refunded back to the externally owned account. So now I'm surprised that nobody has asked me. I keep saying transactions, code, all of these interchangeably. It must have got confusing for you. I will clarify what I exactly mean by a transaction. But just before that, we're talking about accounts. So let's just, I just want to talk about one quick thing. Every account has several fields, right? We saw it here also. We have several fields here. So what do these fields exactly mean, right? There is a nonce value. I'm just talking about the main field. There are definitely more fields than this. There's nonce, balance, storage hash, and code hash. Nonce is a number that increments like 1, 2, 3, 4, 5. It's number that tells you if it is an externally owned account, it will basically sequence the transactions that are initiated from that account. So this is basically to avoid replay attacks and to get the ordering of the transactions right. So let's say that let's say I want to first transfer some money to Bhavya and then transfer some money to, let's say, my mom. And I want it done in that exact order or something like that. So I would give a nonce value of 1 here and then a nonce value of 2. So the blockchain also takes it accordingly. So in every state of an account, the nonce of the next available transaction, for the next transaction, what nonce value should you put? That is stored in the nonce field. For a contract account, this doesn't really make sense because they're not initiating transactions. So the contract account will have other values like how many contracts it has created, things like that. Let's assume that nonce value is 0 always for the contract account. The balance field. Balance, as I said, both the contract account and the externally owned account can have a balance. So whatever balance it has, This balance is only the native token balance. Don't confuse it with any other tokens. It is always in ETH. The amount of ETH that is associated with the contract account or the externally owned account is stored in the balance field. Now, storage hash. If it is a contract account, the contract is a piece of code that will have a lot of variables and other state elements, right? What you're actually storing in the blockchain. So all of that is stored in something called a trie, and the root of that trie is saved here, right? So that is storage hash. This is only applicable in case of contract account. It doesn't make sense for externally owned account because externally owned account has nothing to store. It just has the balance. Now code hash. If in case of contract accounts, the smart contract code, the full, not the variables that it has, the entire code is just hashed and put here. For contract accounts. For externally owned accounts, again, this doesn't matter. It is just the hash value of an empty string. So I hope you can understand that. Maybe I can also give it as notes or something, but the recording is always there to understand this better. Yes, Bhavya, is there a question?
So there's questions. Will the external accounts hold Ether, and will that need any gas for transactions?
Yes, all these balance that I'm talking about is only Ether. It is no other currency. The balance is only in Ethers.
And they're asking about the significance of nonce, and is it usually called a wallet address?
Significance of nonce is just
and
to prevent.
Same as the wallet address.
What is same as the wallet address?
The nonce.
No. Wallet address. So by wallet, I think you mean the externally owned account. The externally owned account has a corresponding public key, right? The public key is basically the wallet address. Okay, you can understand it like that. The wallet address is the public key of the private key. Now for contract account, you take a, let's say this is like a 256-bit string. The contract account also will have an address of a 256-bit string. It's just that it doesn't have a corresponding private key. That is the address. Address is very different from the nonce. Nonce is just a value that basically says two things. How many transactions have initiated from that wallet, and it is basically used to prevent replay attacks. Let's say that I have signed a transaction and I've sent it in the network. Now somebody listening on the network can just take that message, take that package, save it, and keep posting it again and again. It has my signature, so everybody else will accept it. But my funds will keep getting depleted. Let's say I'm transferring 10 ethers. 10 ethers is really long. Let's say 10 GUI to Bhavya. Somebody in the network has just captured this transaction and they're repeatedly sending the same transaction to the network. So I'm repeatedly sending Bhavya 10 GUI and my funds are just getting depleted because that transaction has my signature in it. So how do you prevent that? Every transaction that has to come out has to have a different nonce value in an incremental fashion. If my first transaction was 1, the second transaction I do has to have 2. Third transaction has to have 3. That is that to prevent replay attacks, we use nonce. Is that clear? And for contract accounts, it doesn't make sense. Only for external accounts, this makes sense.
Yeah. There's another question. If you can explain what is the storage tree?
So yeah, I'm just coming to that. That is literally the next slide.
Got it.
Shall I proceed?
Yeah.
Okay. So let's coming to the storage hash. So in a contract account, so contract, you can think a smart contract is basically like a class in object-oriented programming, right? You have member variables and member functions. So the functions operate on these variables and some many external input parameters. So the variables are basically the state that you are protecting. That is the decentralized storage that you're protecting. So now this storage has to be saved somewhere in a way that it is efficient for reads, right? Any data structure that you take, that is that you have studied so far, every data structure, why do you have so many data structures. They're all optimized for different reasons, right? Some are write efficient, some are read efficient, some you want to read and write, so you want the best of both, or you make certain compromises on in one side to get more benefits on the other side. So every data structure has basically tweaks this read efficiency and write efficiency on some scale. That is what data structures do. So here in Ethereum, you are storing so many, imagine how many wallet addresses and how many contracts are there on the Ethereum blockchain. And immediately, if a validator has to execute some function on some contract, he should be able to retrieve that code quickly. He should be able to retrieve the state of that contract very easily. So it's very important that these any account or any information that is stored on the validator's end should be read efficient. I hope that is clear. So a very efficient read data structure is called a trie. Okay, trie is basically a way of storing something such that you can retrieve it in the quickest possible way. So now I have a trie here. Just an example. I'm not going to go deep into this because you can please, there are so many YouTube videos that explain what tries are. So it basically stores a set of words. Imagine a dictionary, right? You store a dictionary, let's say telephone numbers or something, let's say dictionary, and you need to retrieve a word from the dictionary as somebody is typing it. So the word to is stored as T and O. So this is an end. So we have 7 entries that end on this point. Okay, there's just a word so that end, you have one leaf which has 15 entries at this point. So what I'm trying to say is, if I'm looking for a string called, let's say, at, okay, I want the word at, I can quickly say if it exists or not. So I'll immediately go along the A, and I don't see there's nothing else below that. So the word at does not exist. If there is a word at, then A would have another letter T, and there would be an ending point here. So very quickly, I can see whether the word at exists, and if it exists, I can retrieve it also very quickly. So this is what a trie does. There are different implementations of a trie, and Ethereum uses this trie data structure literally everywhere. It just doesn't get bored of tries because it stores states as tries. It stores the storage of basically accounts. All the possible accounts in Ethereum are stored in a trie data structure. Every account, if it is a contract account, it has a separate storage trie data structure. Every transaction is stored as a trie data structure. Every receipts of transaction, there is like logs that you do, like emits, event emits, or whatever. Anything that you want to log out of the transaction, that is also stored as a trie. And basically, because it is so good at retrieving data, the read efficiency is so high in tries, Ethereum uses it everywhere. Okay, does that answer the question? Is there a question, Bhavya? I can see the icon.
Yeah, there's a question. If contract account is an ERC20 token which holds value of Ether in it.
So what is the question? Account is?
If contract account is an ERC20 token which holds the value of Ether in it.
The contract, let's say, okay, there is a contract that represents an ERC20 token.
I think there's a confusion in tokens, protocols, and accounts. Even I'm trying to make it out of the question. Okay. So these people are like actually confusing.
Guys, I have not introduced the word token yet. I'm not speaking in tokens at all. Forget tokens for now. There is a native currency called Ethereum, and the balance, everything till now is stored in Ethereum only. Accounts are basically public keys or some kind of hexadecimal string that you use to uniquely identify your account. That is, let's say you go to a bank. How do you have an account number, right? That is basically the account. That account number has a balance with it, and that will be the balance element here. Right? The address of the account has a balance. The balance will be in ETH format. There is no, I haven't introduced tokens at all. Is that clear?
Yes, I think that should be clear. And there's
Okay.
another
And,
question.
you also wanted a protocol, right? I don't know where I
Yeah,
used the
yeah. Because
protocol.
I think they were confusing the 0x address with the protocols and token addresses and nuances as well.
Okay, so again, I don't know what you mean by protocol, because to me, a protocol is like an algorithm. It is
Yeah,
some steps of doing something.
right.
That is a protocol. When I use protocol in some other sense, I will tell you that I'm using it in a different sense. But if I'm
Yeah,
talking about protocol now, it means a set of steps.
got it. There's another question if the storage hash is related to the Merkle tree.
Yes. Okay. So basically, this tries of Ethereum are a modified trie. This is a normal trie. You can go Google it. The tries of Ethereum are Patricia Merkle tries. And the root of these tries, that is basically this root, is hashed and stored in this field.
Got it.
Okay.
I think they got a little confused by external accounts. So they're asking if you could like briefly explain that as well.
So external accounts, two types of accounts in Ethereum, external and contract accounts. Contract accounts are smart contracts. Any smart contract you deploy to Ethereum will get a contract account, which is capable of storing a balance. Externally owned accounts are basically your MetaMask wallets or any kind of wallets that you have that have a private key. You have to, any transaction you do, you have to sign via your private key. That is your externally owned account. Any transaction on Ethereum has to be initiated from an externally owned account. From an externally owned account, you can invoke some function in a contract, but the contract cannot initiate a transaction because somebody has to pay gas for it. And that can only come from an externally owned account.
Yeah, I think that's pretty clear.
Okay. There are newer technologies now, like we have gasless transaction where a contract pays for you. But even those transactions in Ethereum, everything has to be initiated from an externally owned account. Okay. So, okay, now we spoke so much about how Ethereum internally works. We know what EVM does. We know how data is stored and retrieved on each validator's node when they are re-executing every transaction. Now we're talking about what is a transaction, right? The transaction has several aspects. There is a nonce in this transaction, which is basically this nonce. Every transaction, as I said, is initiated from an externally owned account. And the externally owned account has a nonce value that represents the number of the next transaction that is originating from that account. So that nonce is basically the same as this nonce. For every transaction, the nonce of the externally owned account, the sequence of the transaction that is originated from that externally owned account, that is a nonce field. Is there any confusion in nonce? You were saying that somebody asked a question. Is that clarified or? Okay, I assume it is. The gas price, as in how much are you willing to pay for every unit of gas for this transaction? The gas limit is how much gas units will this transaction actually take? The address. So this address, so again, a transaction, an externally owned account can invoke a transaction from another externally owned account, or they can invoke a smart contract, or it can be any of those two. So the address, the person you are targeting or you want to send something to, right? That is the address. So this address could be another externally owned account or another contract account. The value is the amount of ether. This is always in ether. The value field is always in ether. It is how much. So take a simple transaction, that is from my Ethereum account, I want to transfer 10 GUI to Bhavya's Ethereum account. So the nonce value will be whatever number, serial number of the transaction that I'm doing from my account. This is, again, you already know how much I'm willing to pay and how much units it actually costs. The recipient address would be Bhavya's address, and the value will be 10 GUI. And the signature is what I'm signing for this transaction. Again, I think Bhavya has dropped off. Sorry, guys, this is going to a really long session, but I just have few more slides. I'll cover 5 more and stop for the day, and we can do the rest next week. Okay, so there are 3 types of transactions in Ethereum. Hi, Bhavya.
Hi, sorry, I think there was a drop in network.
It got cut. Okay, so I was just telling them how I would transfer 10 GUI to you. But now, so coming back to the session, there are 3 types of transactions in Ethereum. One is value transfer transactions. That means I'm just want to transfer some ETH to somebody else, one externally owned account to another externally owned account, just by transferring some native token. So here the nonce value would be whatever the nonce value is from the origin externally owned account. The gas price and gas limit is fixed, as in how much you're willing to pay and how much it actually costs. So the gas for a transfer transaction, for a value transfer, the gas limit, that is gas, is always 21,000 gas units. Just to transfer some money, doesn't matter how much money you're transferring, just to transfer, it will cost you 21,000 units. The recipient account is the other externally owned account I'm transferring this money to. The value is how much I'm transferring, and the data is empty because we're not doing anything else. So this is basically empty, and you have a signature. So this is the first type of transactions you can do in Ethereum, which is a simple money transfer. This you can do in Bitcoin also. There is no program element involved here. The second type of transaction is a contract deployment transaction. Okay, so I have written a smart contract. Now I want this smart contract to basically go to be embedded, to be deployed on the blockchain, such that anybody can invoke it at a future point of time. I want all the validators to basically store this code in their system. So I'm just sending a piece of code to the blockchain system. So here, how will the transaction look? The nonce will be, I have written this smart contract, I am deploying it. So it's coming from my externally owned account. The nonce value will be whatever the number of transactions I've done so far. The gas price is how much I'm willing to pay. The gas limit is how much it actually costs to deploy the transaction. So this is not fixed for contract deployments. So depending on the number of functions or what the complexity of your contract code, this can vary. Now the recipient address, here you're just sending it to the blockchain. You're not sending it to anyone in particular. So the recipient address would be null, right? And the value would also be, this can be 0 or it can be something else. If it is not 0, then that much amount of Ether is transferred from your externally owned account to the contract account. When this contract is deployed, it will have a contract address, right? So to that address, this value of funds will be initially deposited. This is the value field. If you have populated this field while you're doing contract deployments, that's what that is the amount of money the contract will have after it is deployed. The data or payload is basically the entire bytecode of the contract that you're deploying. Okay, and obviously your signature saying that yes, I authenticate this deployment. So this is the second type of transaction. The third type of transaction is the contract interaction. That is, you've already deployed a contract. Now you want to invoke a function from that contract. So when you're invoking a function in that contract, basically, again, nonce, I'm invoking something. So the person who deployed the contract need not be the person who invokes the contract. I hope that difference is clear. So the nonce would be, as an invoker, what is the how many transactions I've done so far from my externally owned account. Gas price is how much price I'm willing to pay for this interaction transaction. So the gas limit is, again, how much for that function. Each function will have its gas limit. If it's a very complex function that I'm invoking, then the gas limit changes accordingly. The recipient address. So now I'm basically trying to communicate with a contract. So the address of the contract account address is the recipient address over here. And the value is if that function needs a value, that function needs some money to execute, or if you need to send based on the logic of that contract, if you need to send some ether, then you put a value here. Otherwise, this value is 0. Okay, but if you don't know what that function does and you still send some value, it will get debited from you. And if the contract is not a good contract and they don't refund it back, then you just lost your money. So be very careful when you have to invoke a contract. You need to understand exactly what the contract function does and to know whether you need to send something in value or not. Because if you don't send, then you lose your gas. If the contract actually needs some money sent and you don't send it, you waste your gas money. But if it doesn't need and you still send, then you are wasting your value money. So you need to be very careful. The data or payload contains the arguments that you are sending to the function to invoke it. Right? So these are the arguments that you're passing to that function. And again, your signature. So I'll stop here for this session because we've taken almost 2 hours now. I'll just leave you with this thought. In the rest of this course, we're going to deal with a 10,000 feet view of what I've shown here. But I'm not going to talk about several aspects like this. So we are going to only focus on this interaction. So we have an Ethereum network here. It's a P2P network. They have several validator nodes. And we will be entering this P2P network via some curated nodes given by some service providers like Infura or Alchemy or QuickNode. There are several service providers that give you an entry into the blockchain via their node. They have already deployed Ethereum validator nodes, and you can send your transactions through them. They're the entry points. We'll be using something called Alchemy. Alchemy is a node provider. So we will develop our smart contract code in a language called Solidity. We will compile and deploy it. While deploying it, we need to pay some gas because, as I said, contract deployment is also a transaction, and all transactions need some gas. And we will create a externally owned account via MetaMask. We'll populate some funds, and we will use that money to deploy this transaction. And we will also interact with the deployed transaction on this network, and that will also cost gas, and we will do that via this. Now, if you want to create a full-fledged DApp that is beyond the content of this course, so you will need other things like you can use Web2 architecture, like you can have a backend server that runs a Node.js. You can have a MetaMask, the backend server can contact your contract directly on Ethereum, again via a node provider. Or the MetaMask your front-end application can, React application can talk to the backend application, and then you can have different combinations, right? So we are not going to do that. We're not going to build a DApp, but this entire web process, right, of smart contract deployment and interaction, we will cover in this course. I'll leave you with this thought. I wanted to cover MetaMask, Etherscan, and faucet creation and remix. We didn't have time today, but definitely we will cover it in the next session. So I hope the fundamentals are clear to you, and every jargon that you use to hear in the space kind of fits in your understanding of how this whole thing works. And yeah, I'll stop here for now. I hope till we meet again next week, you are able to revise on whatever is taught, and please have a set of questions ready to when we meet next.
Yeah, I think that was amazing. Thank you so much, Ovia. And if we have any questions, we can just quickly take them. Final remarks before we leave. Okay, so everyone is saying thank you for the session, was very helpful. Thank you. That feedback helps Ovia as well structure it better, I think. Amazing. I think, yeah, everyone loved it. They don't have any more questions as of now.
Awesome, awesome.
All right. Yeah, thank you everyone for joining.
Guys. Good night. Yeah. Hope you enjoyed the session.
Good night, everyone.
Until next week.
Yeah. Bye.